Well, thank you. Thank you very, very much. This is very, very meaningful. I want to begin by expressing my deep appreciation to the nominating committee and the executive committee and the association at large for this tremendous honor. I'm especially proud to join my collaborators and friends who previously received the Lifetime Achievement Award, Bill Woods, Martin Kay, Lowry Cartonen, and Joan Bresnan. I'm going to see if I can get a little bit more light here. Can you still hear me, or do I need to? Okay. Okay. So let's see. So the people that I just mentioned have profoundly influenced. Whoops, that's not good. How did that? There's a lot of machinery up here. Yeah, this is it, but I don't know what happened. Okay, so I want to go back. Yeah. Okay. Let me continue. So they have profoundly influenced the contributions for which I think I'm being recognized today, as have many other colleagues and students that I've worked with very closely over the years. I'll follow the tradition set down by most previous LTA recipients by describing how events in my personal history propelled me towards the concepts, theories, and algorithms I have helped to develop and have become known for. Quite different, I think, from a talk setting forth some current technical result. But, if you don't know the history, they say you're doomed to repeat it, and I wouldn't want anybody to repeat this history. And, I know for most of you, I suspect these are topics that I'm going to talk about from a long time ago in a galaxy far, far away. Some former recipients, Martin Kay in particular, were intrigued by language from a very early age. That was not the case for me. I started as an undergraduate at UC Berkeley with a major concentration in physics. I decided at one point that all that reality stuff was a little too messy for me, and I also discovered that I was not interested in spending long hours in a laboratory. So after a year or so, I switched to math. That carried me forward to the middle of my fourth and final year when I began to contemplate a future as a mathematician, and that also seemed a little dry and unappealing. I thought I would look around, even at that late date, and maybe find a specialization that was a little more social and, for me, a little more engaging. I mentioned this to a friend during a brief ride in an elevator. He told me about a professor in the psychology department who was offering individual majors in what he called language behavior. The major wasn't actually inside a department, so no prerequisites at that late date, since it combined material from psychology, linguistics, philosophy, anthropology, and maybe even mathematics. That sounded pretty good to me, so I went to check it out. The professor, Dan Slobin, was an expert in child language acquisition, and as I later learned, child language acquisition played a prominent ideological role in the newly popular approach to linguistics, transformational grammar. The field was brand new. It didn't have the long history of other disciplines, and therefore not a lot of material to be mastered before jumping in. And I realized that this was a really neat application of formal mathematical methods to a collection of humanistic problems. All to the good, I signed up. I also decided to take the few remaining courses that I needed to complete the mathematics major. So at that point, I had become, if only by accident, a mathematical psycholinguist. I encountered a few high-level ideas during that undergraduate period that have reverberated throughout the course of my career. Chomsky's aspects of the theory of syntax had appeared just a few years before. It provided some formal details of the first main revision to the basic machinery of transformational grammar, but that wasn't what struck me, so now I'm going to do this. Rather, there was a simple statement at the beginning of aspects that set forth a particular view of the relation between a speaker's knowledge of language, the result of learning a language, and the ability to put that knowledge to use in comprehension and production. He said, no doubt, a reasonable model of language use will incorporate as a basic component the generative grammar that expresses the speaker-hearer's knowledge of the language. But this generative grammar does not in itself prescribe the character or functioning of a perceptual model or a model of speech production. This is a clear statement of what became known as the competence hypothesis. I understand it as making two claims. First, that a representation of linguistic knowledge should play a causal role in the mental processes of everyday communication by language. And second, that linguistic knowledge was only one of many components of a larger model of language performance. The first claim, I thought, distinguished this application of formal description from the way that mathematical characterizations are deployed in most other sciences. The sun, for example, behaves according to the partial differential equations for energy transport, but presumably it does not solve a representation of those equations in order to decide what to do next. But the proposition here is that the psychological system encodes and then interprets something that correlates with generalizations about the properties of language that emerge from linguistic investigation. That would be a very neat state of affairs, I thought, if it were true. The second claim places this in the context of another powerful conception, the notion of a nearly decomposable system that Herb Simon put forward in a short essay called The Architecture of Complexity. Simon argued that apparently complicated systems, if created artificially or through an evolutionary process, are likely to be recursively decomposable into collections of separate components. Such systems appear complicated because these components interact in non-negligible ways, but those interactions are relatively simple compared to the interaction of elements within the individual components. It is thus fruitful, Simon would say, to construct scientific explanations of such systems by treating each of the components independently at first, and then layering on top an account of their interactions. Chomsky's statement was consistent with this kind of decomposable architecture, although I think he never got around to the layering on top part. But that became the focus of some of my work. In any event, I was awarded my double major undergraduate degree, and despite my, and I was admitted to graduate school at Harvard. You will have noticed that my story has so far not mentioned computers or computation. I had been involved in computing during my physics period. I had a summer job once computing the fluorescent signature of a high-altitude nuclear explosion, which was a very big deal in those days. And I had taken numerical analysis courses as part of the math curriculum, but there was as yet no connection between computing and language behavior. I had finished up at an odd time in the spring of 1968, and so there was a 6-month interlude between leaving Berkeley and starting up at Harvard. I went home to Los Angeles to look for a temporary job. In another chance encounter, another friend with a connection to the Rand Corporation told me that Rand had a linguistics group and that maybe I could hook up with that. I sent in my papers, went for an interview, and I found that they did, in fact, have an interest in mathematical psycholinguistics, of all things. That really surprised my parents. And they hired me to come on as a 6-month intern. Dave Hayes was the head of a group that included Martin Kay, and Lauri Karttunen was there just finishing his dissertation. You may know that Dave was one of the founders of our field. He coined the term computational linguistics. He helped to create the American precursor to the ACL, and he was involved in setting up the international Coling conferences. He was also a very smart man, in many ways ahead of his time. He was an early advocate of dependency grammar, for example, as a counter to transformational grammar and immediate constituent approaches. And in my case, I remember that he strongly urged me to learn about regular languages and finite state machines. Having read Chomsky's syntactic structures, I knew, of course, that regular languages were totally uninteresting. And coming from Berkeley, I thought that the acronym FSM meant Free Speech Movement. But I did spend an afternoon trying to learn at least something about finite state machines. For my first project, Dave sent me down the hall to work with Lauri on some semantic issues. As I recall, Lauri and I still don't have clear memories. Our computational task was to implement a semantic network within a RAND time-sharing system. I was also involved in Lauri's linguistic investigations into some properties of noun phrase reference, the context in which definite and indefinite descriptions can be properly used. Semantics turned out not to be so hard. I went back to Dave after a few months and told him that we had finished that project. We now wanted to add on a front end to make it easier to interact with our system. He told me to go down the hall in the other direction and see what I could get from Martin Kay. Martin had developed a parsing program that was not based on transformational grammar, but seemed expressive enough to recognize the patterns of natural language. It was a system for rewriting sequences of trees into sequences of trees with Turing machine power. But it used a very efficient data structure called the chart to hold the intermediate state of the computation. There was a missing ingredient, however. Martin had the program, but he didn't yet have the English grammar to drive it. That became my project for the rest of the summer. And that was how I learned about parsing, and that was my entry into computational linguistics. The summer came to an end, and I reverted to my psycholinguistic studies at Harvard. My advisor was Roger Brown, probably the preeminent figure in child language acquisition at the time, and language acquisition was still a focus, particularly at Harvard. So, as a first experiment, I decided to see whether 2-year-olds were able to make some of the definite-indefinite reference distinctions that Lauri and I had worked on. The experiment failed. The children ignored both what I said to them and also the rubber duckies that I had given them to play with. So on the basis of that experience, I decided that I didn't have the patience or interest needed to work with children, and I shifted over to adult comprehension. As per Chomsky, any of you who have worked with children or have children know the problem. As per Chomsky's suggestion in aspects, psycholinguists had a theory of comprehension that incorporated transformational grammar as the repository of linguistic knowledge. They tested the simple assumption that if that were the case, the complexity of sentence comprehension ought to be proportional to the number of grammatical transformations that applied in the linguistic derivation of a sentence. This idea, called the derivational theory of complexity, received some initial support. It appeared in early studies that passive and negative sentences involving 2 transformations were more difficult for people to process than simple declaratives. But later experiments showed the opposite effect. application of an additional transformation had the effect of reducing psychological complexity. The transformation that moves an adjective, a predicate adjective, into a prenominal position makes the sentence shorter and easier to process, even though it's longer in a derivation. By the late 60s, psycholinguists had more or less given up on the derivational theory of complexity. In fact, they had basically given up on Chomsky's suggestion that a model of performance would incorporate a representation of the native speaker's linguistic knowledge. They began to operate independently of linguistics to form heuristic models of language behavior by generalizing just from experimental results. To summarize experimental results in a collection of what they called perceptual strategies. One strategy, that the first noun-verb-noun sequence in an English sentence is taken as the agent, action, object, worked for simple actives, but not for passives, thus accounting for the fact that passives seem to be harder to process. The problem, of course, was that this did not explain how passives could be understood at all. There was no obvious back-off in that theory. Although the derivational theory of complexity did not work out, retreating to a collection of disconnected perceptual strategies seemed like an overly weak response. The problem, I thought, was not in the general conception laid out in the competence hypothesis, that systematic knowledge of language should be incorporated in performance models. Rather, the mistake was in choosing a grammatical framework, the transformational formalism, whose processing characteristics were so obviously unrealistic. Mainstream linguistics was locked onto that formalism, but I knew from my work with Martin and his parser that there might be other sufficiently powerful alternatives, and perhaps some of them might be psychologically plausible. My reputation as a grammar engineer followed me from Rand to Cambridge somehow. A project was starting up at both Beranek and Newman to build a natural language interface that would enable lunar geologists to access geophysical data on the moon rocks that had been brought back from the Apollo missions. Bill Woods was leading the project, and one of the system's key components was the augmented transition network parser that he had developed. An ATN grammar consists of a collection of finite state networks, each of which describes how a phrase of a given category can be realized, and a recursive control that allows for one phrase to be embedded in another. The transitions are augmented with actions that can store information as local variables called registers, and registers are passed forward to condition what may happen on later transitions. Whenever a network transversal reaches a final state, information in the local registers is used to build a tree intended to imitate the deep structure that a linguistically motivated transformational grammar might assign to that constituent. I took over the task of extending an English grammar written in the ATN formalism, and that was my contribution to the first version of the lunar question answering system. Bonnie Weber joined us and extended the semantics and other features for the second version. And a really neat thing is we got to go to the lunar receiving lab in Houston and look at the rocks that we were answering questions about. The ATN formalism also had psycholinguistic potential. In the natural order of execution for the transformational formalism and also for Kay's rewriting system, the outer loop runs over grammar rules encoding separate syntactic generalizations, and the inner loop runs over positions in the input string. That seemed psychologically implausible on its face. It pits the needs of the language learner against the needs of the language understander. In contrast, the natural order of execution is reversed in the ATN. The outer loop traverses a surface structure for the input string, and within that, an inner loop applies only the grammatical options and constraints that are relevant at each phrasal position. I wrote an early paper describing how the ATN parser and a simple ATN grammar could be organized to model the complexity predictions of some of the perceptual strategies. Those strategies could be simulated by carefully fixing the order of arcs leaving a state and using depth-first backtracking for recovery when a chosen arc does not lead to a successful traversal. My colleagues, Eric Wanner and Mike Maratzis, and I investigated the ATN modeling approach in a different way. So these relative clause sentences are equal in terms of their grammatical complexity, and they both express essentially the same predicate-argument relations, but clearly they differ in their psychological complexity. The ATN uses some special actions and a special memory, the so-called hold list, to handle the long-distance filler gap dependencies in relative clauses and questions. The different nouns in sentence A get stacked up in that memory, perhaps overloading it, while in B, early nouns get removed before later ones get added. We proposed that the hold list is a particularly costly psychological resource, and we set out to test that hypothesis. One set of experiments was enough to get me a PhD. These sentences are identical except for the embedded verbs, told and failed. By virtue of the different lexical properties of those verbs, the hold list is empty at the word stop in A. The patrolman told the driver to stop, but the hold list still contains a representation of the driver at that point in B. If the hold list memory is expensive, processing load should be higher at stop in B than A, and the difference should die out at exceeded. This prediction was borne out using a reaction time monitoring task as a measure of transient processing load, and a variant of these sentences with a few more words inserted to compare the region of contrast. And the effect size here was 35 milliseconds, and that's what got me a PhD. And I wish the experiment had only taken 35 milliseconds instead of a year and a half. So that's why I'm no longer an active psychologist. Let's see. I'm going to move on from that. Yeah. In my thesis, I also articulated a particular architecture for performance models with components that were relatively independent and could be studied separately along the lines of Simon. Such a model, I argued, should include a grammar and some formalism, a processor that interprets that grammar, an agenda of order and preference specifications to govern a presumably non-deterministic search, and a vector of coefficients that map processor computational resources into predictions of cognitive load. The individual components should be evaluated as to how well they fit into an overall model, but they should also be evaluated as explanatory artifacts in their own domains. Thus, the grammar, as a repository of linguistic knowledge, should be a revealing encoding of linguistic generalizations, while the processor should admit of a well-engineered implementation. A combination of linguistic and implementation considerations led me to propose some basic changes to Bill's ATN network framework. As I mentioned, the internal state of an ATN network traversal was recorded in a collection of local registers. These were converted to deep, that's what I want to do. These were converted to deep structure trees at the end of a valid path for compatibility with more common linguistic theories. I noticed that information was often lost in this conversion because it was overlooked in the specification or because there was no natural place in a tree for some of the features to reside. Moreover, the parser contained a lot of extra code for constructing these trees from the registers at the end of each traversal, and it had additional tree walking code to inspect those trees at higher levels of recursion. So all of that could be avoided by changing the representation that was produced at each level of recursion and for the entire string. Instead of converting into tree structures, just take the collection of registers encoded as an attribute value matrix as the output of the parsing process. This is the technical source of the functional structures of lexical functional grammar and the feature structures of other unification formalisms. A second observation motivated a further substantial reduction in the inventory of actions and conditions that could be used to set and test the values of registers during a network traversal. A parade example of ATN elegance is the conventional way in which passive sentences can be related to their corresponding actives. The noun-verb-noun in the active become the subject, predicate, and object. The first noun of the passive is also hypothesized to be the subject, but the registers get swapped around when the passive verb sequence is encountered. In the end, the active and the passive are assigned essentially the same attribute value structures, where the subject and object values denote the logical arguments of the predicate kiss. An attractive aspect of this analysis is that it involves no backtracking and over strings or recomputation of phrases, just the ability to switch register values. The perceptual strategy complexity difference could be attributed to this extra fix-up computation. This elegant solution breaks down in the face of tag questions. So Mary kissed John, didn't she? John was kissed by Mary, wasn't he? The pronoun in the tag agrees with the original surface subject, not the logical subject, whether the main clause is an active or a passive. The initial settings of that register must be preserved if the tag is to be analyzed correctly. Other instances of register setting operations also seem to be problematic, and there seemed to be no justification for the full suite of ATN register manipulating operations. The set of register actions and conditions could be replaced by one composite operation defined to merge two attribute value structures, provided they do not contain conflicting values. I call this the same predicate. And this was the seed of the equality predicate of LFG and the unification operator in Martin's functional unification grammar and other formalisms in that tradition. Now, my early ATN account of perceptual strategies relied on a carefully tuned fixed ordering of arcs leaving each state in the grammar. Mailer and Carey conducted a really quite trivial experiment that suggested that this was not a good arrangement. Still thinking about the psychological reality of transformational grammar, they wanted to see whether listeners were sensitive to differences in surface structure grouping, as in A, and differences in deep structure relations, as in A and B, as in C and D. Without getting into the details of their experiments, they found that a sentence of one type, say A, is easier to process after just presenting 10 sentences of the same type rather than priming with 10 sentences of the contrasting type B. It seems that the comprehension strategies can be influenced by very immediate, short-term syntactic experience. Yet we would not want to say that the listener's knowledge of English is so unstable and changes so quickly. Rather, preference orders should not be embedded in the grammar, but encoded as an independent and perhaps rapidly fluctuating overlay. This is the separate agenda component of the modeling architecture that I have sketched. And as an aside, I think there's a question for the integrated models that people talk about today. that such short-term variability poses a conceptual challenge for at least psycholinguistic models that might be based on modern probabilistic and deep learning approaches if preferential and structural factors are so tightly coupled and even indistinguishable. That was the end of my stint at Harvard. I've mentioned a few core ideas that emerged from these really simple psycholinguistic and computational considerations. The compositional architecture for performance models with separate knowledge, process, and strategy components, hierarchical attribute value structures as an underlying representation for syntax, a single same operation for imposing constraints on attributes and values, and a fourth idea that I haven't gone over, that the psychological system includes a memory for previously recognized constituents. And that idea evolved into what we later called active chart parsing. So these ideas are the background for much of my later research. I met Danny Bobrow while working on the Lunar project. He was the vice president for AI at BBN and nominally Bill's boss. He left BBN to create a language understanding group at Xerox's new research center in Palo Alto, and he invited me to join the group. Being a little wary of industry, I asked him how long before Xerox expected us to impact their products. He replied that we were a long-term investment with a 15-year horizon. That sounded safe. I suggested that he also invite Martin Kay so that we could continue our productive collaboration, and Martin and I arrived actually at the same time in the fall of 1974. As the language understanding project started up, we set to work on different components of an overall system. Danny and Terry Winograd worked on knowledge and reasoning, while Martin and I worked on syntax and morphology. This was all in service of a common goal, developing a conversational user interface that would stand in contrast to the graphical user interfaces that others at PARC were exploring. We expected that turned out to be a lot easier, the graphical, the GUI. We expected to assemble the separate components into a prototype system after a few years of work, and we eventually did lash the components together in, again, a Simon-esque way, and in particular, we assigned a student, Henry Thompson, to deal with the non-negligible interactions of components so that we, the principals, could protect the simplicity of our individual modules. The result was GUS, an early mixed initiative frame-based dialogue system that we described in a 1977 paper. Martin and I had the luxury at PARC of examining fundamental computational linguistic issues over several years without otherwise showing much incremental progress. Martin and I argued at length to identify and converge on the most primitive and abstract operations for parsing, and we had long, stimulating, and really quite enjoyable debates, he's a great person to argue with, about the nature and implementation of grammatical formalisms and syntactic representations. We agreed on attribute value matrices as the basic encoding of structure, and something akin to this same idea as the primitive descriptive device. But we had different and strongly held views about how to proceed from there. Roughly, Martin was attracted to the idea that the grammar itself could be coded as an elaborated feature structure, and that parsing consisted of applying implicitly a same-like operator unification to combine the grammar's matrices recursively with attribute value representations of the input words. The effect is to minimize the number of representations and entities as Occam's razor would suggest. But for me, again, taking Herb Simon as the guide, I maintained a separation of grammar as a system of constraints in its own formalism. The use of explicit trees to represent the hierarchical traversal of surface constituents and attribute value matrices only as the underlying representation. I thought of the same predicate as just that, a predicate that candidate feature structures did or did not satisfy, and not a structure creation operation defined by a sequence of computations. I would say that I tended more towards model theory side of the logic, and Martin tended towards the proof theory side. He developed his conception into functional unification grammar, and I will describe in a few minutes how the formalism of LFG derived from the approach that I was parsing. But first, a few words about morphology. On either approach, we knew that the parser needed a front end for morphological analysis and dictionary lookup. Suffix stripping routines for English and similar languages were commonplace, but we set ourselves a more ambitious goal. We wanted a universal system, one that could work not only for suffixing languages, but also for languages that displayed the full range of morphological variation. Lowry Karttunen was consulting with us at Park, and he made sure that we did not overlook the morphological complexities of Finnish, known to be one of the worst-case languages. Linguistic treatments at that time were specified in the generation production direction as cascades of context-sensitive rewriting rules. They started from abstract lexical and morphological formatives and applied rules in sequence until an actual word emerged. A rule of this form specified that a string in a regular language, alpha, can be rewritten to a string in beta if it appears immediately after a left context lambda and is followed by a right context rho. We needed an algorithm for running individual rules backwards and then inverting the entire cascade. This turned out to be a hard problem. The code for interpreting individual rules, let alone the entire cascade, looked to be much more complicated than the code for syntactic parsing, and we knew that couldn't be right. Syntax, we knew, was hard, and morphology is easy. There had to be a trick. We realized that the expressive power of such a morphological grammar is drastically reduced if an individual rule is not allowed to apply to its own output. In that case, the input-output mapping defined by each individual rule could be computed exactly by a finite state transducer. And we knew that a finite cascade of rules could be simulated by the composition of their equivalent transducers. Knowing that there exists a transducer equivalent to each rule was not the same as knowing how to construct such a transducer for a rule automatically. We struggled with that problem on and off for a number of years. For any rule, we could go to the whiteboard, fiddle around with states and transitions, and eventually end up with what looked like the target transducer. But even a simple rule would end up with quite a few states and a large number of crisscrossing transitions, and we almost always would leave out a transition or two, or maybe even a state. Standing back, we saw that the actual transformation, the alpha goes to beta part, was easy. The difficult part was to recognize all and only the occurrences of the context lambda and rho, and to assure that the transformation only took place when surrounded by the proper contexts. This is what took several years of fooling around. After those years, I had one of those aha moments lying in bed on a Saturday morning. Our problem, abstractly, was to translate a universally quantified specification, a rule, into basically an existential device, a finite state machine. Framed in that way, there was an obvious analogy to the simple and direct equivalence between universally and quantified and existentially quantified formulas in first-order logic. Double negation is the key, and happily, regular languages, but not regular relations, are closed under complementation. So this regular expression, by analogy, defines a finite state machine that rejects all strings containing a lambda that it's not followed by a bracket, an angle bracket marking a left context occurrence. With that formulation, we were able easily to implement an automatic compiler for rules of arbitrary complexity and rules of different types, and prove that the resulting transducers have the desired input-output properties. We solved the rule translation problem and composition problem in the early 80s. At the same time, we realized that the lexicon could also be treated as a regular relation and could be composed at the top of the rule cascade. There was then no need for a separate dictionary lookup code. The end result is an efficient one-step reversible mapping from surface strings to lexemes and morphological features. From a psycholinguistic perspective, this exemplified an alternative way of relating competence, the morphological generalization of rule sequences, to performance, the equivalent transducer, compilation instead of interpretation. We have dual spaces with completely different principles of optimization, different strategies for runtime execution, and different properties of computational psycholinguistic resources, but they compute the same mapping. We languished in our efforts to write up these results because of other distracting targets of opportunity. As it turned out, this technology was not only useful as a parser component, it had many standalone applications. We carefully engineered the finite state algorithms, and together with John Maxwell, we developed exceedingly compact ways of encoding large transducers. In 1985, the technology was first deployed in aftermarket spell checkers for the installed base of Xerox electronic typewriters. So with respect to Danny Bobro's description of the 15-year product horizon, I'd like to point out that we came in about 5 years ahead of schedule. We subsequently created a family of handheld spell checkers, conjugators, thesauruses, and even electronic books, all based on this technology. Eventually, in 1994, Martin and I got around to publishing a description of our theoretical results, and I was very pleased to see that it was nominated for the 25-year award. So that was very gratifying. Finite state morphology was a productive and valuable detour from the central concerns of syntax. A year after I moved to Park, I went back to Cambridge to participate in a series of cross-disciplinary workshops that George Miller and Morris Holley were organizing at MIT in celebration of the 100th anniversary of the invention of the telephone. They invited me and my colleagues, my Harvard colleagues, other psychologists, philosophers, computer scientists, and a number of traditional linguists, and that's where Joan Bresnan and I met for the first time. The workshop met once a month over the course of a year, with each group having a day or so to present their work. Eric Wanner, Mike Maratzis, and I described our psychologically motivated alternative to transformational grammar in one session. In another session, Joan introduced the conception of lexical redundancy rules as a better way of describing many syntactic phenomena within a transformational framework. We chatted in the breaks and gradually came to see some common interests. She saw that the psycholinguistic considerations, and perhaps even the one-step mapping, the non-derivational organization of ATN models, could serve as possible supports for her redundancy approach, and I realized that lexical redundancy rules could solve some residual explanatory problems that surfaced in ATN grammars after register operations had been reduced to same. We actually met again here in Italy in the summer of 1977, down the road in Pisa. Antonio Zampoli organized the 4th International Summer School in Computational Linguistics, and Joan, Lowry, Martin, Ava, and others were invited to teach. My course was called Computational Psycholinguistics, and I covered the psycholinguistic modeling approach I have outlined. Joan's course was on realistic transformational grammar. We sat in each other's courses, went out drinking afterwards, and we saw that our work connected in more and more ways. If any of you were there 40 years ago, you may remember how upset Antonio was when Joan and I got deep into a theoretical discussion when we should have been looking out at the beautiful countryside from the rooftops at San Gimignano. So after that, I arranged for her to visit Park. She arranged for me to come to MIT in the following year. We agreed to teach a course together called Computational Psycholinguistics. We agreed that we would do psychology, computation, and linguistics in the same formalism no matter what. We started with the formalism I had developed at Park, and the main challenge was to demonstrate convincingly that linguistic generalizations could be captured in that formalism and those representations. Week by week, we had to make adjustments. In some cases, we had to sneak in adjustments to the adjustments that we had announced just the week before. The pressure from linguistics helped to clarify the fundamental notions that lay at the core of the syntactic architecture. I developed a completely declarative interpretation to replace the lingering procedural aspects of the formal setup. The surface constituent structure and the deep functional structure are represented formally as structures of different types. And again, in a Simon-esque way, they are responsible for characterizing different aspects of the sound and meaning mapping. But both are seen as models in the mathematical sense for type-specific collections of constraints. The constituent structure, grammar, and lexicon provide a description that a functional structure must satisfy, given the assumption of a piecewise correspondence between nodes of the tree and units of the attribute value matrix. The power to characterize non-context-free dependencies comes from the fact that the same predicate is respecified as ordinary mathematical equality with its recursions, and the C structure to F structure correspondence is many to one. So this briefly summarizes the formal foundation of lexical functional grammar, and what emerged at the end of that course has been extended and refined in subsequent research, but this picture of the underlying architecture is still accurate after 40 years. Is anybody keeping time? Oh, I can keep, well, I'm over already? Okay. So I will briefly mention two other things that evolved from this. One is a new parsing system that we developed at Park, myself and John Maxwell. The problem we had to deal with was that this was now even further abstracted away from concrete computation in its mathematical formal setup. So now the question was, how do you bring in computation again? And we did the obvious thing. We did a unification for the equality, and we did context-free chart parsing for the phrase structure, and we did the simple bottom-up pruning that people would typically do to put them together. It was effective, but it was really a computational disaster. So we worked on that problem to try to understand where the exponential was coming from. It was coming from two places. One was that there were Boolean combinations of the equations that we'd come up with, and the other was that the equations were being generated from the tree structures of the context-free component, and you had to enumerate the trees in order to get the equations, and the grammar could be exponentially ambiguous. So we worked on the first problem on the intuition that in natural language, even though there is a worst case, in natural language, it's unlikely, we thought intuitively, that constraints that are far away from each other, that are distant in the tree, are likely to interact. So if you go to disjunctive normal form, you're betting that they're going to be inconsistent and you can throw things out. But the proper bet is to bet on independence and to go for a conjunctive normal form. And we found a particular, after many years of fiddling around with algorithms and trying to figure out what are they actually computing, we came up with this trivial lemma that has a two-step, two-line proof that if you have a disjunction between a bunch of formulas, alpha or beta, that's true if for some new Boolean variable p, p implies alpha and not p implies beta is true. And that, if on the assumption of independence, the Boolean satisfiability problem reduces from 2 to the n to n times 2 to the k, where k is much less than n. And that happens automatically if this hypothesis about language is correct. So we were interested in this formula here of ambiguity management and not resolution. And in particular, this formula allows you to pass representations that are packed representations of ambiguity in one component across a module boundary to another component without actually enumerating or disambiguating. So you could avoid premature disambiguation and avoid the exponential explosion while you kind of passed structures over to a component that maybe had more solid information about how to proceed. So we built a system which we call the Xerox Linguistic Environment. It's a very high-speed, broad coverage interpreter for broad coverage grammars. We then created a project called the Parallel Grammar Project to build those grammars. And a lot of people were involved in building substantial grammars, very robust commercial-grade grammars for English and a bunch of other languages. And it was interesting that it takes about 2 person-years to build a high-performance grammar, and you compare that to the time that it took, for example, to annotate the Penn tree bank, which is about 10 years. There's this trade-off in there that I think is quite interesting. So that system and those grammars became the basis for PowerSet, this system that we did, spin-out from Park that we did for semantic search that was acquired by Microsoft and went out into the world. I also actually should mention here that, just for context, that Chris Manning worked on the grammar initially. He was one of our students. And Stefan Riesler and Mark Johnson later added a stochastic disambiguation to the system that was very, very effective. So I'll just close with a few more remarks. I left Park for PowerSet when our language technology seemed ready to scale for practical applications. And I've moved still further away from my original intellectual home of psycholinguistics. So I now, in a way, think of myself as a fallen psychologist. But maybe someday I'll climb back. So a few comments at the end. So recently, conversational systems have come into focus as a killer app for computational linguistics. I have argued as a technical leader at Nuance and Amazon that sophisticated natural language technologies are crucially needed to improve the fairly poor performance of the conversational systems that ordinary people are now encountering in their everyday lives. The rapid advances in machine learning, particularly the varieties of deep learning models coupled with the massive amounts of data that can now be collected, are obviously making major positive impact. But I don't think that will be enough. There are some influences on behavior that are accessible by introspection and scientific analysis, but not by direct observation, echoing or perhaps reinterpreting what Ling said yesterday. Learning by observation, even when possible, may not be the most complete or most efficient way of acquiring knowledge of language, human interaction styles, specific application domains, or the world at large. Curated repositories may be easier to create in some cases, or even already available. So returning to one of my persistent themes, we should assume, I think, that conversational systems are nearly decomposable and that the components, some known and some yet to be discovered, are of wildly different pedigrees. Going forward, I think the outstanding scientific and practical challenge will be to characterize and implement their non-negligible interactions. It will take every arrow in our quiver to construct conversational systems that are helpful, informative, and pleasant to interact with. Thank you for your attention, and I want to close again by thanking the selection committees and the association for this tremendous honor. So,